afternoon. Thanks to everyone for attending this presentation. So first, I want to introduce briefly about my company, Linton. Linton is a equipment maker for Ingot and Wafer. We have facilities in China and in USA, as well as in Vietnam. And these are some of our facilities. We have more than 2,600 employees worldwide, and we have an annual revenue of more than $1 billion US. So these are some of our products. You can see that we make crystal growers. Every year, last year, we made more than 8,000 units of crystal growers. And we also make other equipment. This is a semiconductor-grade crystal growers. We also make wafer slicers and the ingot machining equipment. So this is some of our manufacturing shops. And this chart shows the growth of the solar industry from the year of 2000 to 2040. You can see that every year, basically, the solar installment has been increasing. And the last year, there is about 450 gigawatts installed worldwide. And this year, it's expected that about 580 gigawatts will be installed. The solar industry has been increasing very drastically over the past 25 years. And this is the silicon crystals and the wafers for solar. And every year, more than 3 billion kilograms of crystals are produced for solar purpose. And more than 60 billion silicon wafers are made each year. And there are more than 50,000 crystal growers and more than 100,000 crystal growth related jobs. And the typical wafer specs is, the thickness is about 130 microns. And the dimensions is typically 182 times 182 millimeter or 210 by 210 millimeter. So which is M10 and G12 respectively. And each produces about 8 to 11 watts of power. And the current price is about 15 cents to 25 cents US dollar each. So this is a typical machine for crystal growth. Okay. So this is CZ crystal grower. And if you look carefully, you can see that this is actually a very large machine, because if you compare with the person standing on top of the machine and the person standing at the bottom of the machine, you can see the machine itself is about 15 meters high, okay, and about 20 tons in weight each machine. And this is a crystal growth shop with about 1,000 crystal growers. And this is a crystal produced by our machines. The one in the center, on the left side, is a G12 crystal, which is about 800 kilo in weight, and about 5 meters long. And the ones on the right-hand side is a M10 crystal, which is about 7 meters in length. Okay, so can you, yeah. This is a little video shows.
Linton KX was the first to design, develop, and manufacture the current industry standard 1600 size model crystal grower, and is developing the next generation 1700 size crystal grower. Linton KX has delivered over 10,000 crystal growers, proving our ability to efficiently manage the supply chain and increase our scale in manufacturing, servicing, supporting, and improving the performance of our crystal growers. Those qualities, combined with our intelligent one-touch growth control system, has enabled Linton to become a reliable partner, helping customers expand production and improve efficiency. Linton also offers intelligent manufacturing automation for smart factory solutions. The company is committed to providing one-stop solutions for photovoltaic whole-line equipment for worldwide customers from the United States, India, Russia, the Middle East, Southeast Asia, Japan, and South Korea. This has promoted the establishment of international strategic cooperative partnerships that have brought about practical results. As Linton goes global, it also is having a positive impact on the world's photovoltaic and semiconductor industries.
So this short video shows you the scale of a real ingot and wafer manufacturing factory. So this time, I think India has several projects which is trying to introduce this ingot and wafer industry, which I think is a very good move.
Linton KX was the first.
Okay, so this shows the different models of the pullers or crystal growers we make. So from a very small one, which is called CT3000, to a very big one, KX380. So the big crystal grower compared with the smaller ones we produced 15 years ago, it's one grower is equivalent to about 10 growers in production capacity compared with 15 years ago. So for the past 15 years, there is a big progress of the production technology. And this chart shows the size, comparative size of the crucibles we use. And you can see that in 2007, which is about 16 years ago, the crucible is about 16 inches, very, very tiny one on the left side. Okay, and now, the ones we use is about this size. The biggest one is about 42 inch. Okay, so the smaller one to the big one, so there is a very large increase in charge size. So which is about, I think, 30 or 40 times increase. And also there is a big increase in charge size, how much each grower can grow the crystal. So in 2007, it's about 30 or 40 kilo. Now it's about 900 kilo. And there is also an increase of the crystal pulling rate. So the crystal now can grow a lot faster. And this chart shows, okay, how many crystals can each round grow over the years. So in 2007, it can only grow such a small crystal. But now, we can grow big crystals like this. Each round, we can grow 8 or 9 crystals like this. So there's a big increase of the productivity. Okay. And so every year, every month, okay, the productivity, the capacity, or the kilograms of crystals each puller can produce also increased drastically. From less than 500 kilo, now it's more than 5,000 kilo. So the current technology improvement, it's one of the big improvement is that the automation. So now we have so-called one-click crystal growth. So that means that you only need the operator to push one button. The crystal will grow by itself. Okay. Compared with the complex process before, now the growing process is much simpler, so and easier. So it's very important for newer players as those ones in India. And then the automation, it's basically based on the camera, the industrial video, and the artificial intelligence. So there is because of time limits, I cannot go into the details of it. But with the the video by CCD camera, so it can tell, all the process progress, such as this one shows the melting of the portion for the melting of the polysilicon inside the melt. So it shows that whether it's completely molten or not. So that's all automatic process and by artificial intelligence. So this is shows the automatic growth of the crystal. And so because of time limit, I just show some pictures of the automation. So this shows how to detect the facet of the crystal, whether the crystal is in the right shape or not. Okay. And this is also a automation process for facet detection. This shows the diameter calculation, the control of the diameter. So now the best, with our technology, you can control the diameter of the ingot within plus minus basically within half a millimeter. Okay. And also this is some details, melt gap measurement. So this is the artificial AI, artificial intelligence, try to improve the crystal growth, and it improves by itself, gradually learning the process. And this is automatic loading. Okay, so also this is in data, big data, and try to analyze the data to improve the production. There are also some more examples. This is an interesting picture because this is a whole plant, picture of a whole plant, crystal growth and wafer slicing. It's a general arrangement for 10 gigawatts. If you can see all those small pictures are the crystal growers we showed before. This is a big plant area, and there is about 650 crystal growers here. It shows the layout of the grower. As I said, the growers each are 15 meters tall, about 20 tons in weight. But in this picture, it all shows very small. So it says that this area is very large. Actually, this plant is about 40 to 50,000 square meters. And you can see that these are the toolers. These are other machines. Okay. Yeah, this for this area, charge area, and cropping area, and the raw materials area, and so on. And this shows, some other, the layout of other areas. So there's the furnace area, and polysilicon ingot machining, gluing, slicing, and sorting and packing. So this is a whole plant layout for 10 gigawatts. So this is about, as I said, 40 to 50,000 square meters in area. So it's a very large area. Many machines, about 1,000 different kind of machines. So it's a big factory layout. So also shows the materials flow. There's also, this one shows the so-called central control room. So all these machines, about 1,000 machines, are controlled by a central control room, and the people sitting in the control room facing the big screen, so that each person can control about 100 pullers. Okay, so that shows the level of automation. And this is also some wafer slicers. Okay, wafer slicing technology. You can see that with our wafers, you can actually slice very thin wafers. The wafers slice, as you can see, this is only about 45 microns to 55 microns thickness. So very thin wafers. Okay, so these are some details of the wafer slicing technology. So because and also automation of the wafer slicing. Okay. So with all those automation, I think there is a big improvement of the cost. So now the cost of the wafer slicing dropped by more than 10 times compared with 10 years ago. So making monocrystal the most competitive technology in solar industry. Okay. So that resulted in the market share of the mono technology to basically increase to a monopoly, about 100%, occupied 100% of the market. So this is some the so-called low oxygen solutions. Okay, so we can get a very low oxygen level below 9 ppm. And so there is a further cost reduction roadmap. Okay, so in the future, the cost of the wafer, ingot and wafer will further decrease. So make it more competitive. So some newer models, the 1700 or 1800 pullers, are being introduced. So because of time limit, I have to run fast. So this is a simple summary. Progress in production technologies assisted the rapid reduction of the cost of silicon monocrystals. And the reduced cost together with the increased PV conversion efficiency enabled the monocrystal wafers to be more competitive and dominate the market shares. And the future progress of crystal growth and the wafering technologies will assist the solar energy to replace traditional energy and reduce carbon emissions. So now the solar energy actually become the most competitive form of power in the world. At this time, I think the benchmark cost is about 1.5 dollar cents per kilowatt hour. So which is cheaper than almost any form of other type of energy. Okay, so that's it. Thank you. Yeah. Okay.
Hello, yes. Sir. Just I want to know what maximum size of a single wafer has been fabricated by your company. Maximum size.
Maximum size of the wafer? Or?
Wafer.
Yeah, the wafer this time, I think it's really dependent on the industry need. Okay, so currently the industry want G12, which is 210 times 210. That's the biggest one in the market. But so if you want to produce, we can produce much bigger ones. The problem is that there is no market for it. Nobody wants to buy it. Okay. For example, we can produce instead of 210 by 210, we can produce 250 by 250, or even 300 by 300. But at this time, there is no market for it. Nobody wants to buy it. And that's the problem. Okay.
Are you developing flexible wafers also?
Maximum wafer size. There is no limit to the maximum wafer size.
No, maximum, no, flexible.
Huh?
Flexible. That can be bent just like a paper.
Yes, if you slice the wafer to be very thin, let's say 50 micron or so, then it becomes flexible. So if it's more than 100, it's brittle. So you just break very easily. But if you slice it, it will be very thin. It's like a piece of paper. Then it becomes flexible. Yeah.
So flexible wafers up to how much temperature it will be stable?
How much
Because
temperature?
some temperature limit will be there for the flexible wafers. What is the maximum temperature it can tolerate?
The temperature, I think.
Especially in case of flexible.
Yeah, so you can do the normal temperature, let's say 100 degrees C or 200 degrees C, is all flexible. Yeah.
Thank you, sir.
Okay.
Yeah, hi, I'm Aaron. So there is a question that I have in my mind. US and China have a strategic leadership in terms of their native ingot and wafer production. India still lacks in that. So what do you think, like, why India doesn't has their own indigenous native ingot and wafer production? Is it the lack of technology transfer, maybe the lack of capex, maybe the lack of skill set, maybe the lack of constant resources like water and electricity? What do you feel like why India don't have their own indigenous wafers and ingot production facility?
So, if I understand your question, you ask why India so far does not have the ingot and wafer technology, right?
Yep.
So I think it's just a little bit slow in adopting the solar energy because China started to do solar in 2005 and 2004. Okay, so it has been about 20 years to do the solar manufacturing. India, I think, gradually caught up. I think India started to do this maybe 5 or 6 years ago, started with the modules, then now moved into the cells. Then some companies now are trying to move into the ingot and the wafer. We already talked to several customers. They have plans to do ingot and wafer. So I think the problem is not whether India can do it or not. The problem is that whether India feel it's the time to do it or not. So now I think it's the time for India to get into it because India has a big market and it have a big demand for solar power, and solar power is good for India. So now it's a time for India to introduce the ingot and the wafer technology, as well as the solar technology as a whole. Okay, so it's time.
Got it. Thank you.
I have a small question. What is the difference in terms of purity of the ingot for a solar wafer and that for a semiconductor wafer?
Can you say the question again? I just
See, you produce the semiconductor wafers
Okay.
also from the same ingot.
Okay.
And,
it's a different. So semiconductor wafer, it's a totally different quality requirement. Okay, and the purity and the quality are all different. One example is that solar crystal typically has the purity about 7 nines. 7 nines means 99.99999. 7 nines. But if you want to do semiconductor, you need to do 11 to 12 nines. So you have to add 4 to 5 nines over there. So it's about 10 to 100,000 times more pure. You have to make it more pure. 100,000 times more pure. Okay.
Thank you.